Hello, in this video we will learn to describe the various flip-flops using verilog code. We will learn to generate the RTL schematic for the various flip-flops. We will learn to write the test bench and we will learn to generate simulated waveforms. Before that, we should know what is flip-flop and what are the various types of flip-flops, right? After that, we will see how to write verilog code for various flip-flops using behavioral modeling. Our discussion will focus on behavioral models. Okay. So, the question is, what is flip-flop? Flip-flop is a memory element that is capable of storing one bit of information. It is also called as bistable multivibrator since it has two stable states, either 0 or 1. Flip-flop have two stable conditions and can be switched from one to the other by appropriate inputs. These stable conditions are usually called the states of the circuit. They are high, that is 1, or low, that is 0. Flip-flops are used as data storage elements. It is the basic storage element in sequential logic. A flip-flop is a device which stores a single bit of data. One of its two states represents a 1 and the other state represents a 0. Typically, flip-flop includes 0, 1 or 2 inputs, more than 2 inputs, that is as well as a clock signal as input and an output signal. Some flip-flop also include a clear input to reset the current output. There are several different kinds of flip-flop circuits with designators such as SR stands for set reset flip-flop, JK flip-flop, D delay flip-flop, T toggle flip-flop. These are the various different types of flip-flop. Okay. Next, modeling flip-flops. In that, first one is behavioral modeling of SR flip-flop. We will see how to write verilog code for SR flip-flop using behavioral modeling. Behavioral modeling is the highest level of abstraction in verilog HDL. We can describe the circuit by just knowing how it works. Here in behavioral modeling, we don't need to know the logic circuit or logic equation. We just need a simple truth table. We need to know how SR flip-flop behaves, right? Hence, let's go through the truth table. SR flip-flop has two inputs, set and reset, S and R, and it has two outputs, Q and Q bar. The Q output is considered the normal output and the output Q bar is simply the complement of output Q. Okay. From the truth table, it is clear that SR flip-flop will be set or reset for 4 conditions, right? For last condition, when both the inputs S and R is equal to 1, it will be invalid state. For last condition, it will be invalid state. Okay. SR flip-flop will be set. SR flip-flop will be set when S is equal to 1 and R is equal to 0. Flip-flop will be reset when S is equal to 0 and R is equal to 1. If S is equal to 0 and R is equal to 0, the first condition, when both the inputs are 0, then previous state is remembered by the flip-flop, no change. But when both the inputs are 1, the last condition, SR flip-flop will be in an uncertain state where both Q and Q bar will be same. This is not allowed since the two outputs should be inverse of each other, right? So this is indeterminate state. This is the logic symbol of SR flip-flop. Next, this is the verilog code or behavioral modeling of SR flip-flop. As usual, first start with the modeling. As always, we start with the module declaration and port declarations. Okay, first start with the modeling declaration. The keyword module. Here, the keyword module informs the compiler that we are creating a functional block with some inputs and outputs. In the parentheses, mention the terminal ports in the logic circuit. Next, declare the input and output ports. Okay, next declare the input and output ports. Here we have to mention output as reg in behavioral modeling. Okay, since we use procedural assignments in this style of modeling, we have to make sure the outputs retain their value until the next value is given to them. Okay, here an always procedural block with event control in the form of a sensitivity list. This is called sensitivity list is used to determine an always block with event control in the form of sensitivity list is used to determine when the state of the flip-flop changes. Okay, if else are case statements in the procedural block are then used to determine the next state. Okay, always block is used to determine when the state of the flip-flop changes. If else statement is used to determine the next state. Okay, the always keyword make sure the statements between begin and end will executed as soon as the sensitivity list is triggered. This is the sensitivity list. Since the flip-flops are memory elements that change state on the active edge of a clock signal. Okay, this is the sensitivity list. The always keyword make sure the statements between begin and end will executed as soon as the sensitivity list is triggered. Here we are designing a positive edge triggered SR flip-flop. The posed clock, here inside the parenthesis we should write posed clock, that is positive edge. Here we are designing a positive edge triggered SR flip-flop. So the pause edge clock in the sensitivity list will make sure the statements between begin and end will be executed as soon as the positive edge of the clock is detected. Okay. Now we describe how we want our flip-flop to work. Right. Depending on the values given to the S and R, we assign our Q and Q bar outputs. Okay, and the if else statements execute the statement depending on the conditions applied. Okay, here depending on the values given to S and R, we assign Q and Q bar outputs. Okay. Next, as per the code, depending on the S and R inputs, the statement for Q and Q bar outputs will be executed. See here, when S is equal to 0 and R is equal to 0, Q is equal to Q bar is equal to Q bar. That is, flip-flop holds the previous state. Our previous state is remembered by the flip-flop when both the inputs are 0. When S is equal to 0 and R is equal to 1, the flip-flop is in reset state. That is, Q is equal to 0, Q bar is equal to 1. When S is equal to 1 and R is equal to 0, then the flip-flop is in set state. That is, Q is equal to 1, Q bar is equal to 0. But when both the inputs, that is S is equal to S and R, 1, that is when S is equal to 1 and R is 1, then the flip-flop is in an uncertain state, right? Okay. This is the verilog code for SR flip-flop behavioral modeling style. Next type of flip-flop is JK flip-flop, right? Another type of flip-flop is JK flip-flop. In this, the J input is similar to the set input of SR flip-flop and the K input is similar to the reset input of SR flip-flop. The condition J is equal to 1, K is equal to 1, that is both the inputs are equal to 1, which is not allowed in SR flip-flop, is interpreted as a toggle command in JK flip-flop. The JK flip-flop has two data inputs J and K, one clock signal input clock, two outputs Q and Q bar. When J is low and K is low, the Q returns its previous state value. That is, it holds the current state. Okay. When J is low, see here, when J is low and K is high, then flip-flop will be in reset state. That is, Q is equal to 0 and Q bar is equal to 1. When J is high and K is 0, that is low, then flip-flop will be in set state. That is, Q is 1 and Q bar is 0. When J is 1 high and K is high, then flip-flop will be in toggle state or flip state. Okay, this is the truth table of JK flip-flop and it is the logic symbol of JK flip-flop. Then let's go with the code for JK flip-flop. As usual, first three conditions are similar to that of SR flip-flop, but the last condition, that is when both the inputs J and K is equal to 1, flip-flop will be in toggle or flip state. That is, this means that the output Q and Q bar will complement to the previous state value. Here, this means that output will complement to the previous state value. And this is about JK flip-flop. Module declaration, input-output declarations. When J is equal to 0 and K is equal to 0, output previous state is remembered by the flip-flop, or flip-flop holds the previous state or current state. Next, when J is equal to 0 and K is equal to 1, flip-flop will be in reset state. When J is equal to 1 and K is equal to 0, flip-flop will be in set state. That is Q is 1, Q bar is equal to 0. When both inputs are high, then flip-flop will be in toggle state or flip state. Next type of flip-flop is D flip-flop. It has a clock signal as one input and data has other. Okay, there are two outputs and these outputs are complement to each other. The symbol of D flip-flop is as shown in figure. This is the logic symbol of D flip-flop and this is the truth table of D flip-flop. D flip-flop will act as a storage element for a single binary bit or digit. Q follows D. Q follows D at the clock edge. Okay, and this is the code for D flip-flop. This always statement will update Q with the value of D on the rising edge of the clock signal. Next type of flip-flop is T flip-flop. T flip-flop is also known as toggle flip-flop. Okay, toggle is to change the output to complement of the previous state in the presence of clock signal. The T flip-flop has a T input, one clock signal input and two outputs Q and Q bar. When the T input is low, okay, then the next state of the T flip-flop is same as the present state, that is holds the current state. Okay, when T is equal to 0, when T is equal to 0, that is when the T input is low, then the next state of the T flip-flop is same as the present state, that is holds the current state. T is equal to 0 and present state is 0. T is 0 and present state is 0, then the next state is equal to 0. Okay, and if T is equal to 0, Q is equal to Q, Q bar is equal to Q bar, that is it holds the current state, right? When the T is high, then the next state of the T flip-flop is toggled, that is it is same as the complement of present state on clock transitions. That is when T is equal to 1 and present state is equal to 0, then the next state is 1. That is the complement of present state. When T is equal to 1 and present state is 1, then the next state is 0. Okay. In the next video, we will